Hi guys, so yeah, I'll talk about the Neil Gehrels Swift Observatory, and if this works, what's going on, that's Neil Gehrels, and that's the Neil Gehrels Swift Observatory. You know, I'm standing here giving the talk, but Swift is an awful lot of people. Some of them will get name checks, and many of them won't as I go through here. The brief in the email that Fabian originally sent said the first 2 days are here to discuss current issues, challenges, and opportunities. So I've kind of taken that a little bit as the brief of this talk. And since I get to start this session, I thought I'd start a bit more generally with a few thoughts on the challenges and issues. And I think the top one is my biggest one. Can we have some more binary neutron star mergers, please? As Federico said, we had we've had two actually, because there was I can't see the presenter display. The other one was 190424, is that right? But it had like a 4 pi steradian localization. But then I think Spiasis did find a possible counterpart. Yeah. So, you know, still a few more would be nice. We're not at the level that the rate is like inconsistent with the model predictions. We're just at the level where the rate is really annoying, especially for people who are continually trying to justify telescope timing proposals, because the time is going to come where TACs are going to say, but you're not finding any of these. It's kind of true with neutrinos as well. You know, we have the Texas source that was mentioned this morning, and then there's this other one that's kind of popping up. And then you've got these population studies that say, you know, if you look at the population statistics as a whole, probably a bunch of these neutrino triggers are connected with a bunch of these blazars, but it's all probabilistic. So which one is which, you know, is not something we can say. So it would be lovely to have a few more of those. And I think that's genuinely one of the biggest challenges. I don't know what it was about 2017, but, you know, we got 1708-17 in gravitational waves, and then 1709-22, just in like 6 weeks later. And we all thought, well, hey, multi-messenger astronomy is here. And then it kind of stopped. And I added to this is my phrase. I don't, maybe it's just me, right? But this kind of the other thing that I think is a challenge. I call it impatience fatigue. You know, we were all really geared up when LIGO Virgo started. We were all, you know, teed up, ready. We put all this work, a lot of us, into preparing for it. And the same with the neutrino stuff, which we've been working on for a long time. And then as nothing seems to happen, well, first of all, especially if you're a postdoc or PhD student, you've got to be doing research, right? So you're doing other stuff. I've got other things I'm working on with Swift, and it's really easy to lose the boil slightly and to not be ready when stuff happens. And I am a little bit concerned that maybe, you know, when the next big event happens, maybe some of us who were really raring to go and knew what we were doing the first time around will find that we're half asleep. So, you know, we've got to keep an eye on that as well. On the other hand, you know, and we're going to hear, these are really just teaser trailers for talks you're going to hear this afternoon, I think. But, you know, the gravitational network is, I assume LIGO India is, I haven't heard that that's not still a plan, so I hope that is happening. But we've got O5, we've got the new two, you know, future facilities that we heard about on the ground, and LISA coming, CAGRA is coming along, IceCube is still being upgraded, you're going to hear more about that, Chem3Net is coming very soon, Einstein Probe and SPOM you're going to hear about, you know, we've got new facilities up there. I don't think on the agenda we've got Vera Rubin. Now, okay, Vera Rubin is not specifically a multi-messenger facility, but it's going to find 4 gazillion transients a microsecond. So it's actually going to do us a great job in this field, right? Genuinely, you know, when we get a large area sky map, go and look at what Rubin saw there last time it looked. I think it'll be a good start. The other thing I just throw out quickly here, which I think is a great opportunity, but maybe, is these recent so-called long mergers. So since 1993 and Chris Cavaliotto's seminal paper, everyone who's worked in GRBs has known there's 2 types of GRB. You have the long ones, which are spectrally on the soft side in gamma rays. And those are unambiguously, through many observational constraints, confirmed to be caused by the collapse of massive stars. Then you have short GRBs, which are harder spectrally, and they are associated with binary neutron star mergers. And 1708-17 was like the smoking gun proof of that. And then this happened just a couple of years ago. So this is a paper by Gillian Rastinajad on GRB 21-12-11-8. I can never say that number because it's symmetric, but not the way you say it. But basically, this is like an absolutely nailed on hard, long gamma ray burst. If you look down here, right, it's right in the middle of the distribution of long bursts in the temporal and hardness plane and just in the temporal plot. By anyone's money, this is a long gamma ray burst. But without worrying, I'm not going to details of this now, it also unambiguously has a kilonova association. And the kilonova, as you heard this morning, is the electromagnetic signal from our process, nucleosynthesis, following a neutron star merger. So this looks like a neutron star merger, but it's a long GRB. And then we've got another one as well. You have to read the paper if you want all the details. This is Andrew Levin's paper. But after a lot of work, they confirmed that this is JWST image. That red kilonova there came from that host galaxy there. But again, it was a long GRB seen by Fermi. So this opens up, I think that opens doors for us because it tells us that the potential counterparts to binary neutron star mergers might be a bigger pool of objects than we thought. On the other hand, we're still not finding them, so you know. So let me go on to SWIFT. Fabian gets bonus points here, better than our own space agency for realizing that SWIFT is not an acronym. So thank you, well done. I've stolen this picture off Jamie because it's more fun than the one that I normally show, which is a Lego model of SWIFT. But SWIFT was designed to study gamma ray bursts, right? And it includes one of its big science goals was finding short GRBs and localizing them. So the first short GRB afterglows came through SWIFT. And of course, we also found the UV counterpart to GW170817. But if you think about some of the characteristics that SWIFT was designed with for this, we have multi-wavelength coverage because we have 3 instruments, the hard X-ray BAT, the normal X-ray XRT, and the UV optical telescope, which strangely covers the UV and optical wavelengths. It slews very rapidly. So typically after BAT triggers on a GRB, the XRT and UV are on source within a couple of minutes. It's very, very flexibly planned, you know, deliberately, because it's designed to study new objects. So we don't know today what we're going to be observing tomorrow. So we have planning telecons. You know, SWIFT is planned on a daily basis. We have rapid TRO response. And I'll hammer this bottom one because it's so huge, especially in the modern day now. But all SWIFT data are public, you know, within the moment they arrive on the archive. But the thing is about this is this also enables SWIFT to be really powerful for loads of other stuff as well. Oh, hang on, I missed a slide. There's also a couple of things that have come since launch. Automated analysis, that's kind of my baby, certainly for XRT. So all of our GRB products for the X-ray telescope are online, automated and more reliable generally than you get by hand. So these are not quick look, these are like publication ready analysis. And a whole load of still evolving, very, very efficient software for planning, for the daily planning telecon, for allowing TRO uploads and all sorts of new developments. I've listed some there, but I'll say a bit more about them as we go along. And all of this is really great for more broadly things like TDAM generally. You think about the facilities. So this is another figure that I've stolen from Jamie, which is just the number of TROs a year over time. And I mean, this is just bonkers. Tell me another satellite that does 1,700 target of opportunity requests a year. I mean, that's loads a day. You know, it's 5, 6 a day. And it's great for us that we use it. And it shows the value of it. And the value is, again, the same set of stuff. We have multi-wavelength coverage from the one satellite. Rapid slewing means that once we upload your TRO, we can be on target within 2 minutes, potentially. Flexible planning means that we can get that upload up within hours, hold that thought, within hours of you even submitting the request. We have open data, we have open submission. Any of you can submit TROs. The automated data analysis is not just for GRBs. You can do it on demand through our website or indeed now through the SwiftTools Python module for pretty much any X-ray object you want. And the ground software just keeps getting better and better. You can submit your TROs to an API. We've got all these mass tiling, which I'll show you about. So SWIFT is really, really good for this stuff. And so, of course, we have results. This is the famous one, 170817. I stole this plot of Jamie's slides, but I made it originally, so, you know. I have nightmares about this one still. We talked, Frederick, you said about waiting for night in Chile. SWIFT doesn't have to wait for night. There were specific cases in this event, which you can, I'll tell you about if you buy me a drink. But basically, if I just stuck with what we originally planned, we would have got on target like 12 hours before anybody else. But there was pressure to do something different, and I wish we hadn't. Of course, we don't know if we had got on that early. Oh, crumbs. Okay, if we had got on that early, I don't know that we would have seen anything because we don't know when the UV thing turned on. But anyway, however, the point is we know we can do this stuff. And actually, this is a result you might not have seen, but it just shows the flexibility. There's a fun story here because we were at an XRT team meeting in Florida, and when we were developing this mass tiling, and I was getting a bit of pushback from from the mission director. And I was saying, look, I need to know what happens tomorrow. There could be a GW event that requires 700 targets a day with SWIFT. And I need to know, yes or no, can we do this? And literally the next morning, we had a GW event that requires 700 targets a day with SWIFT. One time my prophecy came true. So this was a fantastic opportunity, and it really shows the power. You can see just up there, the amount of area we covered. 718 fields in 24 hours, nearly twice as much in 2 days. And then just after that, the trigger was retracted. So, you know, never mind. It's a good proof of concept. But I believe that SWIFT is still the only satellite that can do this kind of thing this quickly. I know something like Einstein probe can cover a large area sky because it's got a much bigger field of view. But this rapid movement, getting around quickly with multi-wavelength, is still something that only we can do. Neutrinos, in one sense, are a lot easier because, you know, this is some of our neutrino follow-up patterns. This is 7 tiles and this is 37 tiles. So we can cover neutrinos. It's still actually a challenge to, you get a lot of data to analyze. And we have been following neutrino follow-up actually since we started off with doing doublet events with IceCube, and now we follow up the high energy ones. Of course, a lot of the problems with neutrinos are depending on the emission. There could be instantaneous EM and neutrino emission, or there could be 10,000 years between the two, so it's a little bit difficult to bring its challenges. But we were there when Texas J was discovered, or IceCube 170922. So here's our XRT. This point, where's my thingy? This point over here, that was our first discovery point. We had some historical data. So we were able to put this out as a possible counterpart, and we were on within only 3 hours of the IceCube trigger. And then, of course, Fermi confirmed it, as we know. Just a couple of quick other results you might not have seen. This is from Noel's paper from 2020 over here. So this was a GW event in 2020. It was a binary black hole merger. Now, we don't expect to see, probably, EM signals, but who cares what we expect to see, right? We want to prove theorists wrong. That's the job of observers. But we were able to actually, therefore, although we didn't find anything, place some pretty decent limits on any possible GRB. We only follow up the well-localized BB80s. There was one yesterday. I believe we've covered about 80% of the error circle again for that one. There's other stuff we do. FRBs, I'm going to gloss over this slide pretty quickly because technically it is a multi-messenger, it's multi-wavelength. What I really want to draw your attention to here is I said it takes us hours to get up a TOO, but actually this has come down. Look, 32 minutes and then a couple more in 2020 down there. And in 2023, we got one up in 4 minutes. So this is all basically all thanks to Jamie, who should get a lot more credit than he does. But
2 of those minutes are on the chime side.
There you go. So 1.9 minutes. So, so we've now got this really, really fast capabilities when we want to do it. So new functionality we're developing. I talked about the living X-ray catalog at the last Astro-COLIBRI meeting I was at. So I'm not going to talk about that now, but that's kind of my baby. It's a real-time X-ray catalog with a transient detector. And it found a very exciting event within 3 months of turning it on, and then almost nothing ever since. So that's, again, why the universe does this to us, but it's not just BBHs. We have the guano nitrate stuff that Jim is going to talk about next, so I don't need to mention that. Continuous commanding, or as Jamie calls it, joysticking Swift around the sky. We can pretty much literally just keep telling Swift constantly, go here, go here. So this is really good for this flexibility. And this new case that's just come in, which if you want to know more about, you should talk to Jamie, but we call them emergency zero TOOs, so special case agreements like the Chime FRBs, where it's end-to-end automation, so we can really actually be observing within minutes of some event. We're getting old, but we're still innovating, we're still new, but we have challenges. Again, thanks a lot of the time with some of the anomalies we've had to Jamie's work in fixing the pointings to the antenna and changing the slew model when one of the gyros broke. We're still working. The biggest problem is the solar cycle. While giving you guys beautiful aurorae, I miss them. They always happen just after I've gone to bed. It causes the Earth's atmosphere to inflate. That increases drag. Swift's orbit is decaying at a terrifying rate. Let's move on quick before it hears me. But Swift really is fundamentally, Swift is a TDAM mission, and Swift is perfect for this stuff. And actually, the Astro Decadal Review from NASA essentially said we really need something like Swift to do this. And the only, I feel like a Volkswagen Golf. Do you remember the advert? If you want a car like a Golf, it'll have to be a Golf. Well, actually, if you want a Swift-like satellite, you need Swift. So we're productive, we're going strong. We are, I think, is that the last slide? Yeah, whoops, never mind. We're still funded. Of course, funding is also getting increasingly tight, but as long as Swift is going, we'll be TDAMing. And I'll stop there and take any questions.